Hi, welcome to Office Hours. My name is Patrick Curran, and along with Dan Bauer, we make up Curran-Bauer Analytics. In prior episodes of Office Hours, I've talked about what is growth curve modeling and how do you estimate a growth curve model using a multi-level modeling framework. In this episode, I'd like to spend a few minutes talking about how do you estimate a growth curve model within a structural equation modeling framework. Now, also in another episode of Office Hours, Dan has talked about what are the advantages of structural equation modeling and where might we want to use those. And so very briefly, he talked about how a structural equation modeling framework is an extremely powerful and flexible multivariate methodology that subsumes a whole lot of models that we're already comfortable with. So within a structural equation model, we can do a t-test, we can do an ANOVA, multiple regression, but we can expand those and look at tests of complex mediation and multiple group analysis and a whole variety of other things. One of the truly unique aspects of the structural equation model is the ability to estimate latent variables and then structure some latent variables with other latent variables or with other measured variables in our data set. And this is going to be the key to estimating the growth curve model using an SEM framework. So just to orient, let's pretend that we're trying to assess depression, so depressive symptomatology, and say that we have 5 items that assess depression. And so they might ask an individual in the prior 7 days, how often did you feel sad and lonely? How often did you feel that you couldn't derive fun from activities that you enjoyed before? A real salient item is how often have you felt lonely even in the presence of others? And so we get these 5 items, all right? These are sometimes called indicators on the latent variable. So we have Y1, 2, 3, 4, and 5. Now, all of these 5 items we believe to arise from some underlying latent propensity to experience depressive symptomatology. Now, one thing we could do is we can add up the 5 items, take the mean, and use that as a manifest score. But as Dan talked about in a prior video, there are a lot of reasons why we wouldn't want to do that. It assumes all the items are equally related to the underlying construct, and it assumes there's no measurement error. But what we can do is say, all right, the reason that I believe these items exist, right? They have variances, means, and they have covariances with the other items. The reason that I believe those interrelations to exist is because they share an underlying cause. And what that underlying cause is here is a latent depression. We didn't directly observe it. We believe it to exist, but we can't directly observe it. And we're going to use the information that we did observe about the symptoms of depression that we assessed in our scale to infer the existence of this latent depression. And so as Dan talked about, we can have a variance of that. We can have a mean of that. So we can call that psi and mu. These are called factor loadings. They're denoted by lambda. These are called residual variances. We can call those sigma squared. Each item has a residual variance. And the point of this is to take information about what we did observe and make an inference about something that we believe to exist but did not directly observe. And this is one of the unique strengths of the structural equation model. This is drawn out is what we might call a confirmatory factor analysis model, but we could expand it in any number of ways. Why I start with this is going to be the cornerstone to how we build the growth model. So think for a moment about what I started with, is we believe there to be some underlying propensity to experience depressive feelings and symptoms, but we can't directly observe it, and we want to infer its existence based on what we did observe. Well, that is exactly what we're trying to do with the growth model. If you happen to watch a prior episode where I described what is a growth model, is we can consider, sorry, my pen is dying. Say we have 5 repeated observations on depression again. All right, but now here is age. All right, so say that we have age, whatever, 6, 7, 8, 9, 10, and we have depression. and we observed these 5 repeated observations, we want to fit an individual growth trajectory that may have some kind of starting point. Let's just call that beta naught sub I, and some rate of change we could call, say, beta 1 sub I. That one's done too. And notice these dots are what we observed on our individual, but that's not what we're interested in. What we're interested in is using those repeated observations to identify the underlying latent trajectory that we believe to exist, but we didn't directly observe. And you can see the direct link to the confirmatory factor analysis model. We want to take the information about what we did observe to infer the existence of what we believe to be there, but that we have to infer from the data. Okay? So how do we do that? Well, let's go back now and think about those multiple indicators on a latent factor. But now, instead of 5 individual items on depression, let's say that we're going to examine 5 repeated measures on depression. All right, so we have, again, 5 boxes. Right? The symmetry here is tremendous of what we're going to cover. So here we have, now let's just say it's going to be age 6. So we'll call it Y6, Y7, 8, 9, and 10. So we observe depressive behavior at age 6, 7, 8, 9, and 10. And we have some sample of say, children that we're studying. And what we want to do is use this information to infer the existence of the underlying trajectory. Well, for each component of the trajectory, that is the intercept, a linear component, a curvilinear component, a whole variety of things we can do, the general rule is that for each component, we're going to estimate a latent factor that's going to capture that part of the trajectory. So for example, let's say that we want to build a linear trajectory. All right, so over here, we have a dark line that's going to be the fixed effect. And go back and watch the broader video on what is growth modeling for more detail on this. But we could refer to this as, say, mu alpha, and we can refer to the fixed effect of the slope as mu beta. These are the mean intercept and the mean slope of pooling over all the individuals in the sample. And then we had all the individual trajectories. And the random effects were the deviations of each individual from those means, and we captured those random effects in the variances of those. So we want to build this model. Well, first we have to start with the intercept. We have to begin the process, all right? Now, also in another episode of Office Hours, and you can go back and look at this if you haven't seen it as well, is I talk about rescaling time and where we can put the 0 point. So let's say that we have time as 0, 1, 2, 3, and 4, which is going to be age minus 6 in this example. If 6 is our youngest age, 6 minus 6 is 0, 7 minus 6 is 1, and so on. So what we're going to do to define this, given that time is going to start at 0, is we're going to estimate a latent variable that has all 6 repeated measures as indicators, 5 repeated measures. Notice the exact symmetry so far with the confirmatory factor analysis model I showed just a couple of minutes ago. But here's where the first big difference is when we estimate it as a growth model. Instead of estimating the factor loadings, we're going to fix these to values of 1.0. Each of these 5 factor loadings is fixed to 1. We're going to estimate a variance of the latent factor. Let's call that psi alpha. And we're going to estimate a mean of the latent factor. Let's call that mu alpha. And let's just call this factor eta alpha. So eta is the generic notation for a latent variable, and alpha we'll use to denote the intercept. Okay. Now, each of these items will have a residual variance. So I'll use the little double-headed arrow to denote residual variance, and that's sigma squared. And maybe these sigma squared values are equal over time, maybe they're not. That's a testable hypothesis that we could look at later. The big thing we have here, though, is there are not means estimated in the individual items. So these are sometimes called item intercepts. We're going to fix all of those item intercepts to 0 and only estimate the mean of this latent variable. All right, so we're going to try to reproduce the means and the variances and the covariances among the repeated measures only through the characteristics of the mean and the variance of the latent factor and the residual variance. All right, so this sets up this start of the trajectory. So mu alpha is going to be the mean of the latent factor, and psi alpha is going to be the variability in the starting point. But now we have to introduce a rate of change. If we only had this, it would imply all the lines were flat. There would be variability. Some would be higher, some would be lower, but they're all flat. But here we want to introduce an increase over time, all right, or a decrease depending upon the characteristics of the data. And so to do that, we'll simply estimate a second latent variable. We'll call this eta sub beta, all right? And this is going to go to y 7, 8, 9, and 10. We won't draw it to y6 because the time coding for the first assessment is 0. So there's no influence on the first period. But look at what we're going to do. This will be 1, 2, 3, and 4. And there you see 1, 2, 3, and 4. All right, so that's giving that rise over run. It's just an increment per unit change as time progresses. Now this also has a variance. This is going to be psi beta. It also has a mean. It's going to be mu beta. And then it has a very interesting parameter, which is the covariance between these two, psi alpha beta, and that gives us a assessment of the linear relation between where you start and where you go over time. So for example, in this, how I've drawn this is on average, those who start higher tend to increase more steeply, and that's going to be captured in that parameter. So this SEM, it has all the loadings fixed to 1, these loadings fixed to 1, 2, 3, 4. Only the residual variances are estimated in the repeated measures. And then each latent variable has a mean and a variance and then a covariance between the two define this growth model. We get an average starting point in mu alpha. We get an average rate of change in mu beta. We get individual variability in starting point that's captured in psi beta. So that's the degree of variability in where kids start. And we get individual variability in rate of change. So how different are the slopes across individual, and then this covariance. Now, in a prior episode, I talked about how to estimate this model within the multi-level, and this is identical to what I called the unconditional model in the multi-level. We had a level 1 equation that had age as a predictor, and we had level 2 equations that were defined by means, the fixed effects, and then the random effects. We call them U's, and that's exactly what this is. The big difference between the two, one of many, but a significant one, is whereas in the multi-level model, age is a numerical predictor in the data set, it literally is a column of numerical values in the data file. Here, our data file only consists of the repeated measures, and we're incorporating the passage of time through how we fix the factor loadings. And in another episode, as I said in an earlier episode, I talked about you could have 0 at the starting point, you could have 0 at the middle point, you could have 0 at the end point, and each of those would define a different intercept. All we would do is change how we code these factor loadings. So if you wanted 0 in the middle point, you would have -2, -1, 0, 1, 2, and you would then just simply have -2, -1, 0, 1, 2 on the slope factor. And then that would move the intercept. So you can take a look at that if you're interested in the coding of time. Now this is called an unconditional growth model because we have no predictors. And often we'll use this modeling framework to try to identify the optimal functional form that's needed. Is an intercept appropriate? Is the model improved when we add a linear slope? Is it improved further if we add a quadratic that puts in a curvilinear? We might want to estimate a piecewise linear, where we tie two linear pieces together. An interesting model that we can do here is we don't have to fix all the loadings to predefined values. We could estimate a subset of them to estimate some nonlinear trajectory that doesn't necessarily follow a parametric form, a quadratic or a cubic, something like that. But there are two particular ways that we would like to expand on this model. One is to incorporate time-invariant covariates. Those are characteristics of the individual that don't change with time. And we might want to expand this to time-varying covariates. So those are covariate values that can change with the passage of time. And so both of those are very easy to do in the SEM. Imagine that we had a linear model, and now we want to try to understand individual variability and starting point and change over time. And we had some set of covariates. Say we had x1, and I'll just draw x2. But we could have any number of them. Maybe it's gender, maybe it's alcoholism diagnosis in a parent, maybe it's are they an only child or not. Some characteristic of the child is if they're time-invariant covariates, so we just have one assessment of them, we can just use them to predict the growth factors directly. And what this is going to do is allow us to test for a shift in the means of these latent factors as a function of the covariates. So for example, let's say just as a simple example, we had gender, and we wanted to know, are there meaningful differences in the characteristics of developmental trajectories of depression for boys versus girls? Well, we could regress eta alpha and eta beta on a single binary indicator, and what we might find is that there's a unique trajectory for girls. Let's make that boys to follow theory. Sorry about that. So we have a unique trajectory for boys, and we have a unique trajectory for girls. So this is more consistent with developmental psychopathology, especially if the transition to puberty is on average, girls tend to accelerate in depressive symptomatology, is now boys and girls have their own intercept, boys and girls have their own slope, and those are derived from this influence. It would be the predictor of the intercept would separate the two trajectories at the starting point. The predictor of the slope would push the slopes apart, so that then we would have one for each. And this can be expanded in a whole variety of ways. The other way that we can expand this is to bring in what are called time-varying covariates. So those are predictors in the model that would directly influence the repeated measures instead of dictating the trajectories themselves. So just as one example, we might have a time-varying covariate that was, say, parental divorce. Was in that 12 months, did the child's parents get divorced? And that time-varying covariate, I know this path diagram is getting messy, but there are ways we can draw these that are much better, is it's looking at any given time, was there a bump to the child's depression above and beyond the trajectory process that could be associated with the parents getting a divorce. And so it kind of pokes the individual time-specific value. And we can expand this in a whole bunch of interesting ways. We can have multiple time-invariant covariates, we can have multiple time-varying covariates, we can allow them to interact with one another. There are a lot of really interesting things that we could do. And finally, one last extension that is a particularly powerful characteristic of the structural equation modeling approach to growth modeling is, what if you have growth in two constructs at one time? So let's say, I won't draw all the repeated measures, I'll focus just on the latent growth factors. Imagine that we have eta alpha for depression and eta beta for depression. So this is just intercept and slope for depression. But let's also say that we were interested in a growth trajectory for eta alpha for aggression and eta beta for aggression. All right, so we have some growth model for aggressive behavior. We have some growth model for depressed behavior. And we would like to know to what extent are those constructs related over time. And we can even test a regression of, does initial levels of depression predict changes in aggressive behavior? Does initial levels of aggressive predict changes in depressive behavior? We can then add covariates here that predict the growth factors. We can have time-varying covariates, and then there are a whole series of increasingly complicated models where we can simultaneously look at how do two constructs relate over time at the level of latent factors, but then add on to that also time-specific, kind of autoregressive structures, and there are a variety of ways that we could do that. So, in summary, that is a quick overview of how we can estimate the growth curve model within a structural equation modeling framework. It's beyond the scope of what we're talking about here, but there are a whole class of growth models that are numerically identical if you do them in a multi-level or a structural equation modeling framework. It's arbitrary how you do it. They're numerically indistinguishable. But then each approach also has unique elements where it expands in a direction that the other one is not as well suited to do. And so there are many additional topics we could explore with that. So I hope you have found this of some use, and thank you for your time.